Okay, hi guys. I'll give everybody just a second to get on. Um, and then I'm also going to get my little document camera up and running here. Um, so that everybody can see my document, my little rigged up document camera here. And I realized that I am doing this a little bit earlier than I originally scheduled. I don't know about you guys, but we just got the lovely Smith County thing. So, we're having fun with that and making sure it's all going to happen there. Like I said, I will get everything posted up. My plan is for us to cover 3.4 and 3.5 in this session. I do know that Zoom is now limiting me to 40 minutes. So I'm going to try and get through this in 40 minutes. If it looks like we're going to have to go longer, then I will set another meeting. And I will get that Zoom ID posted so that you can see. Usually I like write it on this document, on my little document screen thing, and I try and, well in advance, and then I cut one meeting and I immediately start in on the next one so that everybody's got a chance to do that. So for section 3.4, the first thing that we're going to talk about is, and I'm going to switch views here, is the rational zeros theorem, okay? Now, the way that this reads is it says if you have a polynomial, okay, where you've got this a sub n x to the n, and then you've got this a naught back here at the back. If p over q is a root, okay, so they're specifying that this already is a root, it's a solution, it's a zero. All those phrases, root, solution, zero, all mean the same thing, okay? It's where it hits on the x-axis. And this is already in reduced terms, so we're not going to do 1/2 is different than 2/4. All of those are the same thing, as long as it is an equivalent version, okay? Then what it says is P is a factor of this a naught, or the constant term, and Q is a factor of a sub n, which is the leading coefficient. Now, yeah. So what we actually do with this is we actually work this in reverse. What we do is we figure out what are all of my factors of a naught, what are all of my factors of a sub n, and then from those we create this list that says, look, if it's gonna be a fraction looking thing. Now, keep in mind whole numbers technically count, okay, because we could write it as 2/1, okay, but again, we would reduce that, okay. We can make this kind of list that says, look, if it's gonna be a whole number or it's gonna be a fraction, it's gonna be in this list, okay. And what that helps us do is it then specifies that it can't be any other fraction or whole number that's in that list. Now, if you remember back to when we did kind of the last example that we did in 3.3, where they said, knowing that -1 is a zero, solve. The problem is, or the condition on that one was, they told us -1 was a zero. Now they're not going to tell us anything. So we kind of have to have a jumping off spot, and I don't want to have to just start randomly picking numbers that are out there, okay? So the way this is going to work, okay, is, and we're going to look at 4x to the 5th plus 12x to the 4th minus x minus 3. Okay, this is our problem. Now, we're going to do p over q. Now, again, factors of p have to come from this number back here at the back. So factors of 3 are 1 and 3. Q comes from up here. So factors of 4 are 1 and 4, 2 and 2. So I'm just going to list those like this. Now, the next thing that has to happen, okay, is we need to partner pair everything on the bottom with everything on the top. Now, I don't care what your method is for how you do this, but you need to have some sort of a pattern. Now, personally, what I do is I pick the first thing on the bottom and I run through the top series. Then I'll switch to the next number in the denominator grouping and then run through the top again. And then I will run through the next one, so on and so forth. Now, the only concerns that we have here is, in order to get this -3, okay, thinking about kind of factors and stuff like that, I don't know if they did like 3 and 1, and one of them was negative and one of them was positive. I don't know how that came about. So when we clean up this list, because we're not going to leave these things in this, you know, like 1/1, 3/1 format, we're going to have to put a plus and a minus in front of each of these items. Okay, so this is now our full list, okay, that we would have to do. Now, one of the things I am going to add an extra example into this because I want you to see what happens when you have some stuff, like what happens if I have a duplicate, okay? What happens if I have something that matches up twice, okay? So I'm going to get rid of this one, okay? And let's do something like 2x cubed minus 8x squared plus 7x minus 6. Okay, so P over Q again. Factors of 6 are 1 and 6, 2 and 3. So we've got 1, 2, 3, and 6. And then factors of 2 are 1 and 2. So I'm going to make my master list. So I've got 1/1, 2/1, 3/1, 6/1. And then I've got 1/2, 2/2, 3/2, and 6/2. So now when we create that reduced list, I get 1, 2, 3, 6, 1/2. Now y'all, 2/2 is 1, and I've already written that in my list, so I do not have to write it again. 3/2 has not happened before, and 6/2 is the number 3. That's already shown up in the list as well. So when it talks about in reduced form, that is going to cut down on the number of things that you have down here. Now, if MathLab has a plus minus button, use it. Okay, otherwise you're going to have to list this as 1, -1, -2, -2, -3, so on and so forth. Okay, and it would become kind of a lengthy list. I want to say that they have the plus minus button, but I don't exactly remember when they did that, okay? So this is, again, P is coming from factors of this back part, and Q is coming from factors up here. If you have stuff that when it reduces is going to create something already in your list, you do not have to write it again, okay? So kind of like the way we've done domain and range. So now the next example that we are going to look at, okay, is going to be where they have us creating this list, finding a 0, and then working. Now, the thing with this is, okay, the whole point of any of this is to get a polynomial worked down far enough to where I can get it into a quadratic formula, okay? Either I can factor it or quadratic formula. So for this one, since I'm at x cubed, if I can find 1, okay, a solution, root, 0, whatever you want to call it, okay, if I can find 1 and I do my synthetic division with it, then the leftover, that resulting answer that's down there at the bottom, remember, it reduces by 1 power, okay? So that means it would come down to an x squared. Once you're down to an x squared thing, you can either factor it if it'll factor, or you can run it into quadratic formula, either or, okay? So the goal here is I got to find 1 first. So again, P over Q. P is factors the back. Factors of 2 are 1 and 2. Q is up here at the front. I don't have anything there, so it's just going to be a 1. It's going to be 1/1 and 2/1. So it's going to factor down to plus and minus 1 and plus and minus 2. Okay, so the next thing that we're going to start to do, I'll move this down just Okay, is I'm just going to start by doing synthetic division. So I'm going to put a 1 in the box. So I'm just starting with the first thing that's positive 1. And coefficients wise, I've got 1, 1, -5, -2. So I'm going to skip and draw. It's going to be 1, 1, 2, 2, -3, -3, -5. Okay, this is not a 0 because I have leftover back here in the back end. Okay, so I'm going to reset. And I'll try with a -1. So I'm just going to try the next one in the list. It's going to be -1. It's going to give me 0. 0 is going to give me -5. It's going to be 5. That gives me 3. Okay, again, not a 0 because I have leftover back here in the back end. So we'll reset and try again. Okay, so we'll go to 2. So we've got, it's going to be 2, 3, 6, 1, 2, 0. Okay, I found one. Okay, so this is one of my solutions. Okay, or it says find all zeros. There's one of them. Now, remembering that this is now x squared x and my number. Okay, this is also ABC if you're going to go into a quadratic formula, which is where I'm going to go. So I've got -3 plus and minus square root of 3 squared minus 4 times 1 times 1 all over 2 times 1. We've got -3 plus and minus, that's going to be 9 minus 4 over 2. So I've got -3 plus and minus square root of 5 over 2. Okay, I realize my video may have just okay, there it goes. So these are my other two. Now, if I've got to list them out separately, okay, I would have 2 -3 plus square roots of 5 over 2 and -3 minus square roots of 5 over 2. Okay. That'll catch up to me here in just a second. Okay. So you would list them just as the 3 separate ones if they asked for it to be separate. Okay. Now, the next thing that comes up in this section. Uh-oh. Where am I? Whee. Okay, sorry. I don't know what mine's doing real quick. Let me check one thing. Oh, that's still good. Okay. We'll come back. Okay. Sit down. Okay, good deal. Okay. Now, a couple of properties that come up with this loveliness. Move this up just a bit. Okay. Is if your degree is in, and remember that the degree is the highest power that is shown, okay, then there are n roots, okay? Now, with those roots, they are not necessarily all different, okay? So for example, if I had something like x to the 5th, la da da da, okay? There are 5 roots, but they may be 2, 2, 2, 3, 3, okay? So I would technically only say 2 and 3, okay? Technically, I would only say 2 and 3, but if I count them separately, I get all 5 of them, okay? Now, the other thing that comes up out of this parts of the properties of roots is if a plus bi is a root, a minus bi is also a root, okay? So complex roots always come in conjugate pairs. Okay, so it's kind of like buy one, get one free. If they tell me one of them, I automatically get the other one as well. Okay, so if they said -3 minus 4i is a root, -3 plus 4i is automatically a root. Okay, automatically get both for free. Okay, now the next thing is what's called the fundamental theorem of algebra. And basically what it says, if you take any polynomial, okay, with degree 1 or higher, okay, if you take that f of x and you set it equal to 0, there is at least one complex root, okay, or solution. Now, basically what that says is, if I have, now, degree 1 is a line. If I take the equation of a line, so 3x plus 7, and I set it equal to 0, I can solve that for x. If you go to degrees that are higher than that, so degree 2, which is quadratic, I can find answers. And there's at least one of them, okay? So when we talk about quadratics, they can have the same root twice, okay, where it only reads as 1. But there's at least one. Now, with them wording this at complex, okay, that is that they handle all of the number types, okay? Complex is the biggest, broadest version that there is. And so therefore, they have to put it all the way up at complex and not be more specific. So for example, it's kind of like me saying, I have a pet. There's a whole lot of wiggle room in what kind of animal I may have, okay? Because it may be a fish, it may be a reptile, it may be a cat, it may be a dog, it may be a rabbit, it may be some other little furry creature. I don't know. But I've managed to say that I have a pet. Now, certainly we like to be more specific when we can be, but, you know, it doesn't always happen that way. So, now, next thing, and I'm going to put this one out there, okay? This is what's called linear factorization. Okay, now, with linear factorization, this is something you are probably going to be given at least a couple questions of this on the math lab thing. I tend to shy away from these on test questions, okay, because they really are something that is you're building up an equation that meets certain qualifications, okay? And so this is something, like I said, you'll probably see it in the homework. I'm not a super fan of it on tests because it's really just kind of doing some multiplication. So looking at the way this one is done, they want a third degree polynomial. Okay, that has -3 and I as roots, and f of 1 is 8. Okay, now, first thing, we want to talk about zeros. They tell me -3 is a root. Roots and zeros are the same thing. We know we have I. We also get -I, okay? And we get this one because it is the complex conjugate. Okay? So now, if you are going to take these and put them into their factors, okay? Now, I'm going to put an A out here in the front, okay? Because I'm going to need to figure that out here in a minute. When you go into factors, you do the opposite. So we're kind of undoing what we saw when we did synthetic division. So if I have -3, think about that. That would have been what was going in the box. Then we would have seen that as x plus 3 in the division. Okay. Now then, with the I stuff, you always treat these as positive. Okay. So we're going to do a -I, and then we're going to do x minus, and then a -I. Okay. So we've got a x plus 3, x minus I, x plus I. Now, when you're having to do this, you're going to have to multiply all this back together. Please start with the ones where the conjugate pairs are, okay? It makes life a whole lot simpler, okay? And from that, if you multiply that out, you're going to get x squared. You're going to get plus ix minus I squared. This is going to be a. We're going to have x plus 3. We're going to have x squared. These two cancel out. That's going to turn into a -1. So we have minus a -1 that's going to turn into a +1. Okay. Now, multiplying this out, we get x cubed plus x plus 3x squared plus 3. Okay, so I'm going to move over a little bit. I'm going to rearrange this just a little back into our traditional order. Plus x plus 3. Okay, now I have not used the fact that f of 1 equals 8 yet. This is where that comes in, okay? I need to figure out what is the value of this a, okay? Is it a 1? Is it a 2? Is it a 1/2? Is it a -3/4? What is the value of it, okay? So I know my answer is supposed to be 8 when we plug in 1. Okay? So we've got a, and that's going to be 1 plus 3 plus 1 plus 3. So I've got 8 equals a times, it's going to be 8. So a is 1. So my final equation would be just the x cubed plus 3x squared plus x plus 3. Okay, so this would be my final answer equation. Okay. Since my a is 1. Now, let's talk about, okay, I'm going to get rid of some of this over here. Okay. Let's pretend that we had gotten that a was -2. Okay. Sorry. Okay, let's pretend that a had been -2. Then I would have put -2 out in the front of this. Okay, and then I would have distributed okay, and I would have distributed it to look like this. Okay, so if a had been any other number, I would have put the a out in front of this equation that we had over here, and then I would have distributed it to get my final answer. Okay, so this was just because we got that a was 1 back over here. Okay, again, may see one or two of these in the homework. I'm not a super fan of them for testing purposes because they do take a little bit of time. And also, I'm more worried about you finding zeros rather than building something back up, okay? Now, the last thing for this section is Descartes' rule of signs, okay? Now, basically what Descartes wanted to do here is, we had the rational zeros that we had started with, and what Descartes really wanted to do is he wanted to kind of figure out what the zeros were, okay? Like how many of them are positive, how many of them are negative was basically his goal. Because if he knew that, hey, there's supposed to be 2 positive zeros and he found one of them, he still needed to look for a positive 0. Or if he knew that there was supposed to be 1 negative 1 and he had found it, quit trying negatives. There's not going to be any more. Okay. So it could cut down the number that he was trying to find or the number of places that he was trying to mess with. Okay. So Descartes' words really strangely. Okay. If you try to read it on paper, it reads really, really weird. Okay. So what it says is for your positive roots, okay, so for your positive ones, it's the number of sign changes in f of x, or the number of changes minus, I'm going to write it, minus an even integer. Okay, now I'm going to explain why he did this. So basically what happens here is, if you remember me talking about complex numbers are not positive or negative, okay, because they aren't in our regular real world, which means I can't count them. But what happens is sometimes, well, they're able to disguise themselves inside of Descartes' thing, okay? So what happens is he's saying, if you count something, and so you count something and there are 3, okay? So you count something and there's 3. Well, what's going to happen here is they may be all 3 positive, or this one may be complex. And guys, if this one's complex, you automatically get its partners. So these 2 are complex. This one is positive. So that's what he's saying by it's the number of sign changes minus an even. So he's taking these 2 away, saying that they are complex, and he's being left with this one that is a positive. Okay. Now, in order to get the negative roots, okay, and this all begins to make a little bit better sense when you see one actually done in example, okay? So this is the number of sign changes in f of negative x, okay? So we're going to have to do that whole plug in negative x and see what happens, okay? Or the number of changes minus an even integer. Okay, so the same kind of stuff as above. Now, again, this looks a whole lot better, okay, when you actually see one done in practice, okay? And I'm going to let y'all know now, because I'm looking at, I've got a few of y'all in here. I will probably have to start another session, because this one's been going on for like 27 minutes, which means I've got about 13 minutes left. If we have to, then I will get y'all what that new meeting ID is and get that one pulled up just as soon as I can after this one and get this reset into place, okay? I just don't know if I can get through 3.5 in like 10 minutes, okay? So taking a look at this, and if you're following along with the one that I have in the PowerPoint, I am slightly changing that problem. Okay, I changed this to a plus sign. Okay, so if you're following along with the one out of the PowerPoint, I did change this symbol to a plus sign, so just that you're aware of that, okay? So now, when we go to count sign changes, okay, it is really, really simple, okay? This is a positive term, this is a negative term. That counts as a sign change. This is a negative term, this is a positive term. That counts as a sign change. This is a positive term, that's a positive term. That is not a sign change. This is a positive term, that is a positive term. That is not a sign change. So there are 2 positive roots, or, and guys, I can subtract 2 off of that, no positive roots, which means there's 2 that were complex. Okay, so that's how that processes through. Okay, so the 2 that it gave up here turned into complex. Now, the next thing, okay, that we've got to do is I need to do, trying to see if I got space here. I'm going to plug in negative x into our problem, and I am going to have to chase all my signs. I realize it's kind of stuck up there. Okay, negative times negative times negative times negative is going to turn positive. Negative, negative, negative is going to be negative. There's another negative, so that's going to go positive as well. Negative, negative goes positive. This negative is going to pull into the front. And then we have this one back here. So if I, okay, count my sign changes, this is positive to positive, so that doesn't count. Positive to positive, that does not count. Positive to negative, that counts. Negative to positive, that also counts. So we have 2 negative roots, or no negative and we get 2 complex. Now, these are not necessarily the same 2 complex that were up here. Now, the other thing that they will sometimes do with this, and I'm going to try and give myself enough space. This over here. Look. Okay. Is sometimes they will ask you to do a chart, okay? And you're doing the positive roots, the negative roots, and the complex roots, okay? So the way that you're going to do this is I'm going to start with taking the 2 positive roots with 2 negative roots, and there's no complexes with that. Now keep in mind what we said. This is a 4th degree polynomial. I expect there to be 4 roots. 2 and 2 makes 4. Now, I could also keep the 2 positive roots, but have no negatives. So guys, kind of what I'm doing here is I'm going this 2 with the 2 options. Let's see if I can pull this over here. I'm doing this 2 with these 2 options. Then I'm going to go back and pick up this 0 with both of these options, okay? So, come back over here. We said these, when we gave up these, they came over here. Now, next option is I have no positives, but I go back to the 2 negatives. Again, these 2 that were given up come over here. And then I do have the option that I may not have any positives or any negatives, and all 4 of them are over here. Now, one thing to notice here is every single line has a grand total of 4, okay? Every single line has a grand total of 4. And so that is one of the things that helps you know that you've got everything listed, okay? Now, what I'm going to do, because they've already popped up and told me that I have very limited amount of time left, is, I'm going to say this is going to start at 4 p.m. 4:05. 45 minutes. I don't need that. Okay. Okay. Trying to get this scheduled for us real quick. I'm trying to get the next meeting set up so that you guys will know what it is, because I'm going to cut this one off. Okay. So if you will write down, the next meeting is going to be 952-488-352. Okay. So this is, I'm going to have to pick up and start another meeting so that we have enough time to cover this other section, because there's no way I'm going to do it in 6 minutes. This is the meeting ID that I'm fixing to do. Let's get that up there a little bit better. So 952-488-352. I'm going to end this session, and then I'm going to restart this next session just as fast as I can, and we'll go ahead and cover section 3.5. Okay, so I'll see you guys in just a minute.